For
Yeah.
grading.
What?
For grading.
For grading, when can I do the grading of research?
In this week, I will
So
complete.
this week's research component will be done. And test 2 is already graded, it will be uploaded today. Okay, so let's. So for our rest of the course, we only have how many days? Today and then Wednesday. Wednesday is the last day of class, right? So last day of class, we didn't plan anything great for the last day of class, but we'll see. If you have any suggestions, we can do something on the last day, like discuss some new research topic or something. But what I have planned today is GPU programming. So just to give a little bit of flavor to GPU programming in the smartphone and some experience with GPU, because that would be important later. So how many of you have experience with coding in GPUs? Nobody? Only one. So which programming language did you use?
OpenGL.
OpenGL. Okay, you didn't use CUDA or OpenCL.
No, CUDA. I also use a little Vulkan.
What, Misha?
Vulkan.
Okay. So here what I'll do is CUDA is typically used for GPUs. OpenGL, OpenCL are also used. OpenCL are used used in Android, but the basic concept is very similar for all these programming languages. So we'll just focus on CUDA and just look into one of the aspects of the GPU programming. So before we go into GPU programming, we need to understand what is the architecture. But this architecture is gone. It does not zoom out. Okay, maybe this is fine. So I'll be using these slides. These are from from NVIDIA. Uh, so we'll talk about what is CUDA. We'll have some introduction to CUDA, some architectures. So these set of slides doesn't really go into the architecture. So I will talk about the architecture in greater detail, and then we'll go into the actual coding. We'll see some examples related to matrix multiplication. Okay, so let's look at the architecture. So typically how GPUs are organized is that there is a host system, and this host system is typically a CPU, right? Maybe an i7 processor, CPU. And then there is a device. So this device is the GPU, is what is called the GPU, right? So this is the device, and this is what is called the GPU. And you have connections in between the host and the GPU device. Right? So you use certain types of interconnects between these two, and these interconnects typically have a very low bandwidth. So these interconnects are used for data transfer, right? And it has a very low bandwidth. So which means if you want to transfer a lot of data from the host to the device, then it takes a lot of time. And typically that acts as a bottleneck for GPU computers. But fortunately, what happens is that you need to do this data transfer mostly only once at the initial stage. So these interconnects are two ways. So you can write from host to device, you can write from device to host also. And this is also used for transferring code as well as data. So when you write host CPU, the code in the host CPU, you designate certain portions of the code that has to be executed by the GPU. And then what the host CPU does is that it understands that this particular portion of code is to be hosted by the GPU. So it transfers the code through those interconnects as well as the data. Now let's go into more detail of this GPU. CPU we know. For CPU we have the processor, the architecture of the CPU. We have the processor. Then we have some L1 cache which is on chip, right? Then we have L2 cache which is so we have L1 cache which is on chip, L2 cache which is not on the chip, but so it's not on the processor chassis, but still on the chip, right? So L2 cache access time is slightly lower than or slightly higher than L1 cache access time. And then we have a main memory which is totally not even on the processor chassis. It's you have to connect the processor to the main memory using some interconnect bus. And this is typically very slow, main memory access. And the organization is the total amount of L1 cache. The total amount of L1 cache is less than total amount of L2 cache and is much less than the main memory. That's the organization in a CPU. So this is the CPU architecture. Right? This is the CPU architecture. On the other hand, this is hard to read, right? Should I use that board or what should I do?
It's not that hard to read.
This is better?
Yeah.
This is better or the board will be better?
No, this is better.
So typically we have this. Now let's talk about the GPU architecture. The GPU architecture is a little bit different. So in the GPU architecture what you have is that you have this device. Let's say this is the GPU, the entire GPU. Right? So what you have is you have cores, GPU cores, multiple GPU cores, and you have a main memory of the GPU, and all this is on chip. Okay? You have the main memory of the GPU. So this is main memory of GPU, and this is shared. Right? Now inside each core you have very small amount of cache, and this is just a single cache. There is no L1, L2 here. Right? You have a single amount of cache, and then you have a very simplistic ALU. This ALU is very simple. So what do I mean by a simple ALU? Simple means that it does not have branch prediction. No branch prediction. It might not, so it may or may not have hardware prefetching. Right? Those kind of optimizations it might not have. So it's just a very simple ALU. Now you have many of these, right? Typically, what you have is you have a 128 core GPU, right? Which means you have 128 of these. Now this memory, which is inside this, the cache memory, is very small, right? It can range from anything starting from 4 KB to maybe 128 KB, right? So typically very less amount of memory. Now what happens is that whenever you have a thread, right, you can take a thread that you want to execute in the GPU and assign it to a block. So these are called blocks. And blocks are, no, actually these are not called blocks. These are cores. Block is a different concept. Sorry, block we'll discuss later. So you can take a thread and you can assign it to a core, right? Now these cores are numbered. Now when you assign a thread to a core, the access to the L1 cache, or no, this is not L1 cache, the access to the cache of that core is very fast. So this particular thread, whichever data it has to work on, should be stored in that cache. If it is stored in that cache, then it's very fast. But if it is stored in the main memory, remember that memory is shared. So whenever this thread, which is running in one of these cores, tries to access main memory, it has to call for process synchronization on all the threads, on the others, all the other threads. So the moment a particular thread tries to access the main memory, all the other threads have to synchronize, stop. This thread accesses main memory, and then all the other threads starts processing. So whenever you have a large number of main memory access in GPU, you lose the advantages that comes with multi-thread in a GPU. So you should model your application in such a way that whichever data a thread works on, that data is not that large so that it doesn't fit in the cache. Right? That is one very important aspect of GPU programming. So this is the architecture. That it's a very basic architecture, but at the base of every GPU design, this architecture is there. So basically, this access is extremely fast, but the access to main memory is very slow. So let's go back to the slides. So there is a host device, which is the CPU, and then the device is actually the GPU. So this is a basic program that runs on the host, right? We all know Hello World. This is one of the basic programs. So what is it saying is that CUDA is very similar to C, except it has some specific keywords so that you can run it in a GPU. So now that Hello World was in the main CPU, right? Now if you would want to run this Hello World in the GPU, how would you run? So that is the simplest extension. So the simplest extension is this. So whenever you have, let's say you want to run something on the GPU, whatever program, whatever code you want to run, you write it like this. So the global keyword, you put the global keyword, then void kernel. So kernel means the portion of the code that has to be run in a GPU core, in a single GPU core, right? That is called kernel, and what items it takes as input. Then when you actually run the code, you use some line of code like this. Now what is the meaning of this line of code, we'll see later. So whenever you run this, then basically whatever is written inside this function gets run in one of the cores, right? If you have a single thread, then one of the cores. If you have 10 threads, then in 10 cores. Okay. So it explains that this CUDA-C keyword global indicates that a function runs on the device and is called from the host code. So whenever you have this global keyword on a function, then that means this function is being called by the host code and it is run on the device code. Now you know GCC, right? Everybody knows GCC. You use GCC to compile C code for a host machine, like the i7 processor or whatever thing you are using. Now similarly, the NVIDIA has come up with a compiler called NVCC. So NVCC splits source files into host and device components. NVIDIA's compiler handles device functions like kernel. Standard host compilers handles host functions like main. So whenever you have this kind of code, the kernel has been compiled by NVIDIA's compiler NVCC, while the main is been compiled by GCC. Right? So there are two different compilers that work on the same code. So now we come to this line of code and we try to understand what this means, the kernel, right? So the triple angle brackets marks a call from host code to device code. So whenever you have this triple lines, so these function call indicates that it's a host code, it's a kernel code being called from the host, right? So here we didn't really do anything, but what you can do is a simple addition, right? You can just have a simple addition. You can have a simple addition called of two integers. So A, B, and C are integers, and you are adding two integers in the device. Now there are many things to note in this simple function. Note that all these are integer pointers, right? A, B, C are integer pointers. First of all, that's the first thing to know. The second thing to note is that add does not return anything, right? That's another thing to know. And the third thing to note is that the result is stored as another pointer. So if I do this in the device code and it does not return anything, how does the host code know about the results? How does the host code get the results?
From C.
Yes?
From C, since the result is stored in a pointer, it can be accessed from C.
But this pointer is stored where?
It's passed from the host, so the host will have it.
Host does not have this pointer. That's the problem. What? So okay. So let's understand the mechanism. So we'll see later in code actually how it's done, but the basic concept is this. Where did it go? The basic concept is this. Let's say this is the host machine, and this is the GPU device, right? Now, in the host machine, before you call the kernel, you have to have copies of A, B, and C. You have copies of A, B, and C. When you transfer the code to the GPU, what you do is you copy A, B, and C and send the data out to the GPU. What the GPU has is in the main memory, it has copies of A, B, and C. And these are addresses. These copies are all addresses. So you do some form of malloc, right? You have to do some form of malloc to the GPU. I think it's not called malloc, it's a different function. We'll see later. So you have to first allocate some memory into the GPU's main memory where you will copy A, B, and C. Now, when a core does this computation C equals A plus B, this variable gets updated. So you only update this variable. You do not, the function, the add function, the kernel function does not update this host code. It only updates the variable that is there in the main memory of the GPU. Now there has to be some mechanism to update the host code values A, B, and C. There has to be some mechanism, some form of mechanism to update the host code values. So what we'll see next is this mechanism, how to update this host code value. So whenever we call this kernel function, it does not update anything in the host. It just updates the variable or the memory location in the GPU main memory. Now you have to have some form of mechanism to update. So let's see what is the mechanism. Yeah, so that is what this is saying, that how do we allocate memory on the GPU? So we have to somehow allocate memory, and then also not only allocate memory but also keep the host copy and the GPU copy same. So host and device memory are distinct entities, as we have seen in the architecture. So device pointers point to GPU memory, may be passed to and from host code, may not be dereferenced from host code. So this is very important. So these pointer values can be passed to and from the host code, right? But you cannot dereference. What do you mean by dereferencing? You cannot apply the star operator to C in the host code, because that star operator will take you to the address. If you apply star operator in the host code, what will it do? It will take you to an address in the host memory. It won't take you to the address to the GPU memory. So if you have a variable C in the GPU, you cannot apply star C in host code. So you cannot dereference. But you can always send and receive values that are present in C location in the GPU memory. And we'll see how a little bit later. Right? So you cannot dereference. Now host pointers point to CPU memory. It may be passed and passed to and from device code, so you can pass the values, but you may not dereference from the device code. That same logic. If you dereference from a device code, it is going to the device main memory. It is not going to CPU's main memory. So you cannot dereference. So this is an important aspect to keep in mind whenever you are writing GPU code. Now, similar to malloc, free, memcopy, right? We have CUDA malloc, CUDA free, CUDA memcopy. So as you see that CUDA is extremely similar to C, just you have new keywords and new functions, and you have to just keep in mind the architecture of the GPU and the CPU. So if you keep in mind the GPU CPU architecture, everything is very simple. So let's see how we can write the code, right? So here we have just written the kernel. This is just the kernel code, and it does not change. It's just 3 pointers, and pointer C is equal to pointer A plus pointer B. But now we have to populate these values, and we also have to get the result in the host code. So how to do that? So that's why we look at main. So this is the main. So what you have here is 3 variables A, B, C, which are host copies of the variables. Right? These are the host copies. Then you have 3 other pointers, star device A, star device B, and star device C, which are devices copy of A, B, and C. So this is the GPU's copy, right? Now what you do is you this is a size variable which says that how much size do we allocate to device A, device B, and device C, right? So then before even executing the kernel or even referencing it, you first apply CUDA malloc, which means that you make space for these three variables, device A, device B, and device C, in the main memory of the GPU. Right? So you first make space. So that's why you use CUDA malloc. And one very important thing to note is there are two starts. Why? See a little bit later. But just keep that in mind. So then what you do is you assign values to A and B, and then you do CUDA min copy. So which means you copy the value which was there at A into device A, right? And you include this keyword CUDA min copy host to device. So what this does is that this allows you to transfer the data from host to the GPU. Right? So that is the link. That is where that is what we can use to transfer the data from host to GPU. So CUDA main copy, you basically you are storing it in device A and you are taking the value at the memory location of A, right? And similarly for B. Then you launch the kernel in the GPU. So you say add 1, 1 and you give these arguments, device A, device B, device C. Note that you did not dereference in the host code, right? You did not dereference. So basically you are giving the addresses. You are not giving the values as input, right? So you are giving the pointers as input. Then once you are done, once the add function is done, you copy the device results back to the host copy of C. So again you do CUDA min copy, and this time you are copying into C from device C, right? And instead of using CUDA main copy host to device, you do device to host, and then finally you free all the three variables. Right? Very simple, extremely simple operation. Okay, so they are not talking about the pointer notation, are they? Why you have pointers?
You're pointing to a whole bunch of memory in each of the cores in the GPU.
What are you trying to say?
I was thinking that the double pointer represents a pointer to a array of pointers, and each of those is where each of the
No, but then they do ampersand device A. So basically, so CUDA malloc, you have to look into CUDA malloc in more detail. So this device A, what is device A? Device A is basically pointing to an address in the GPU device, right? It's pointing to an address in the GPU device. So you cannot really access that address from the host port. Even if you call device A, you cannot really access that. Now, internally what happens, I don't think it's in this slide or in this set of slides. What happens is that there are two tables, no, not just one table, sorry. The host code, or the host keeps a table, right? It keeps a table which says, so each variable that is of the device, right? Each variable that is of the device, it keeps a table, says, okay, device C or device A is in address X of the GPU device or the GPU memory. So this is GPU memory, and device A is at address X of the GPU memory. Now this table itself has an address. This table itself has an address. So when you are trying to reference device A and trying to allocate memory from the GPU, what you are basically doing is you are instead of referring to this line of this line in the GPU memory, you are basically referring to this table. So when you are just referring to this table, then this means that this is the address, right? This is the address of the first line, and in that line there is another address, which is the GPU memory. So that's where you have the 2 star operations in malloc, because you not only have to assign a memory in the GPU, but you also have to assign an entry in the table which maps the address from the host to the GPU. So that is an internal detail that CUDA-malloc uses, that they haven't discussed that in this slide. So that's the purpose of having these 2 stars. Anyways, that's too much detail. You don't really need it. So what they are next doing, what this slide is discussing is that, okay, this is just one thread, right? We have just called one kernel thread. How about what about parallelism? Because GPU is there for parallelism. So they're saying that the solution lies in the parameters between the triple angle brackets. So if you, instead of the first parameter signifies threads, number of threads. So if you have 1 here, then you execute add just once. But if you have n here, you have n instances of add. So the same kernel function will be executed n times, right? So then using this mechanism, we can do a vector addition, right? If A is a vector, we can do vector addition, and we can ask each thread to operate on a specific element, right, on separate elements. So each parallel invocation of add is referred to as a block. So if you have this add function and you invoke that function multiple times, each invocation of the same function is called add. It's called block, right? Now kernel can refer to its block index with the variable block idx.x. Right? Block idx.x is the typical is the particular instance of add. Is one particular instance of add. So if you have 10 add instances, you'll have 10 different block indexes indices from 0 to 9, right? So that block idx.x, that is one particular instance of add. So what you are doing is that instead of writing the previous code, that star c is equal to star a plus star b, instead you write c equals block idx.x plus equals a block idx.x plus b block idx.x, right? Now what will happen is that one instance of add will go to a separate, so 2 instances of add will go to 2 separate cores, and each add will now operate on a different vector element, because each add has a different block ID, right? So if you have a different block ID, then one particular add will work on C0, A0 and B0, and the other other add will work on C1, A1, B1, and these 2 adds will be on 2 different cores. So that's where you can get parallelism. So we write this code, yes, you do, and this is what runs in parallel on the devices. So block 0 works on this, block 1 works on this, block 2, block 3, and all 3 are working on separate cores. Now they are saying that, okay, under this parallel execution, how does main change, right? So instead of having one variable a, b, and c, now this a, b, and c becomes pointers, because we have to use arrays, right? So you understand here the equivalence between pointers and arrays, right? Pointers is the same as arrays, so that's why you can use this and still you can use an array syntax and still get by, right? Otherwise you could have used a separate different syntax here as well. What syntax could you have used? You could have used star, and then within parenthesis you could have written a plus block idx dot x. Right? That is also a valid syntax. Instead, you can use this one as well. So parallel addition. So here define n as 512. So we have 512 instances of add operation, and there are a, b, and c which are pointers. The same pointers device a, device b, and device c. Now instead of just a single integer, we have n integers. We use the same command CUDA malloc div a size. So we are basically just keeping space for this, and then for a, b, and c we do malloc, right? Because we have to allocate space in the host device as well. Then this is just random integers filling up a and b, and then you copy. You do mem copy device a and a. So remember. So now notice there is a change. Instead of ampersand a, we just write a, right? Because now a is itself a pointer. So you do CUDA mem copy, and instead of doing add 1, 1, we do add n, 1, right? Then after everything is done, we do CUDA mem copy back into C, and then we free A, B, and C, which is the host versions of A and B and C, and then we free div A, div B, and div C, which is the devices version of those. So that's how we can do parallel programming. Very simple. Now, so you have multiple instances of add, right? Now you can, so each instance of add is called a block. Now what you can do is you can take this add and divide into threads. You can multi-thread add itself, right? So what you did was you took the host code, whatever you wanted to do with the host code, you took the host code, divided all the 512 add instances into separate add instances, right? So you have multiple threads. Now what you do is you take the add and further divide into threads. So 2 levels of threading, right? So that also you can do. So what you can do is a block can be split into parallel threads. So when a block is split, they are called threads. Let's change vector addition to use parallel threads instead of parallel blocks. Okay, so now they are using parallel threads. So now what they are doing is instead of using block IDX, they are actually using thread IDX. So this is just overriding. So this is thread IDX.x. So each thread of add will have different thread ID. So when you have an instance of add that has a block ID, unique block ID. Now each block ID, whatever threads you have in a particular block, will have a unique thread ID. So you can pinpoint to a particular thread by using a combination of block ID and thread ID. So let's say there is block 0, and let's say it has 10 threads. It will have thread ID starting from 0 to 9. Block 1 will also have thread ID starting from 0 to 9. So thread IDs are same for block 0 and block 1. But if you use the combination of blocks and threads, then you can pinpoint the thread of, or the 5th thread of the second block. That is unique. The 5th thread of the second block is totally different from the 5th thread of the first block. Right? So using a combination of block ID and thread ID, you can pinpoint a single thread. So how do we change it? So again, you have 512 copies. Everything remains the same, except you use the add n comma n. Is this n or 1 comma n? I think it's 1 comma n.
Yeah, it's a 1.
It is 1, right? Yeah, 1 comma n, which means you have 1 block but n threads. Right? You have 1 block but n threads. So now what you need is multiple threads and multiple blocks. So how do you do that? Now what is the difference? What is the difference between having multiple blocks with a single thread, as opposed to having a single block with multiple threads? What is the difference?
Multiple blocks is performing the same operation for different set of inputs, like for an array of inputs. Suppose if we have multiple threads, like if the function is so vast, if you want to split the function into different sections, you want to execute separately, if they can be executed parallelly, then they can be.
So you're saying add function itself has threads. No. So if you look at this code, the main code of this one versus the previous one, what are we doing? We are just doing the same functions, same add function we are doing. But instead of doing n comma 1, we did 1 comma n. So the net operation is the same. And we have 10 values for C or 512 values for C. Right? Previously, in the last code also we had 512 values for C. In this code also we have 512 values for C. What is the difference?
That is run on one processor at a time. Here it is like different processor can.
If you have different blocks, each block goes to a separate process, separate core. What happens when we have different threads, many threads? Yes. There's a very subtle difference. It goes back into the definition of threads and blocks. Blocks you can consider as processes. Processes means they do not share variables. Threads, on the other hand, they share variables, and you can have race conditions. In this particular example, it does not really matter, because threads are operating on separate variables, right? C1, C2, C3, they are operating on separate variables. But if there was a global variable, then multiple threads could have updated the same global variable at the same time. On the other hand, if you have multiple blocks, they cannot update the same global variable at the same time. They will not, because they will have separate copies. They will have separate copies of the global variable. So basically, threads share the heap and the global memory, but blocks do not share heap and global memory. They have the same initial copies. But then they go their own way. So even if you have blocks, they execute in different cores. If you have threads, they execute in different cores. But these threads can update the same variable. So if that is the case, if there is a global variable x that these two threads try to update at the same time, that global variable x cannot remain in your cache. It has to be in the main memory, because both these threads want to update at the same time. They should be able to update the same variable, because they are sharing these variables. On the other hand, if you have blocks, then this shared variable you are not really sharing. You have separate copies. So that global variable can be in the cache, because you are not expecting blocks to update the same variable at the same time. So that's a very subtle difference. So if you have blocks, if you can make blocks in your code will operate faster, because now these blocks do not have the need to go to main memory to update a shared variable. On the other hand, if you have threads, then they will run much slower if these two threads update the same shared variable, because this shared variable now will have to be in the main memory, because both the threads have to update it at the same time. So it's a very subtle difference. Doesn't make any difference here, because you are not really having a global variable. global shared variable in this particular code. But if you had a shared global variable, single variable, which both the threads are trying to update at the same time, then if you have blocks, it's much faster as opposed to having threads. But then the problem is, if you use blocks, then your result will be different from when you use threads. Do you understand this difference? Is that difficult to understand, or do you want me to explain more? So you understand, right? Threads share variables. Blocks have the same copy of variables. They don't really share the variables. Right? So that's the subtle difference. So it doesn't make any difference here, but it will make a difference when you have shared variables among threads. So now they are saying, okay, how about using threads and blocks at the same time? So let's do that. So basically what they're saying is that, let's say you have a huge array and you want to separate this array into blocks. So you have this block 0 to 7, 0 to 7. You have these blocks, and each block has threads. So as I just explained, that block 0, thread 0 is very different from block 1, thread 0. Right? So what it basically does is that it says that this is kind of a two-dimensional array. So blocks are kind of rows and threads are kind of columns. You can view it like that, right? So what they're saying is that we have m thread block, a unique array index for each entry. So you can, if you consider this thread, you can have a unique array index for that. How? You just do thread index plus block index multiplied by m, where m is the width of a block, right? If you consider that block, every block has the same size, right? Because it's the same code essentially, so it has to have the same size. So every block has 8 threads, right? Now if you want to have a unique address to a particular thread, then you just use that thread index x plus block index dot x multiplied by m, the width of a block. So you can access one thread. So an example, no, this is not a very good example. So here is how you can do addition of a matrix addition, right? So what this is saying is that you can, instead of using the thread IDX or block IDX, just use the index as it is defined here. Block IDX multiplied by block dimension dot x. So this gives you the width, right? So then multiplied by the width plus the thread index, and then you operate on that particular element. So this particular thread will only operate on one of the element of the array, right? So what changes do you need to do in the main? Nothing really. So very simple changes. So n becomes a 2048 plus 2048. Now this is a matrix. Now threads per block, you define that it's a fixed size, 512 threads per block. Everything else remains same. A, B, and C. You have copies. B, B, C. You have to make memory for A, B, and C. You have to copy the data into the device, and then except for having 1, 1 or n, 1, you have this, right? N divided by threads per block, that many blocks you have, and then threads per block, that many threads you have in each block. Nothing else changes, and it will work like charm, right? So very simple, extremely simple CUDA implementation. Why bother with threads? You know why to bother with threads. There's nothing to really discuss here. But there are two very important problems of having threads in GPU, right? The first problem is, if threads have a shared variable, the moment threads have shared variable, your GPU is bound to slow down. Is bound to have performance issues. Why? Because now you have to communicate between threads and synchronize threads, and all this communication and synchronization occurs through interconnects between cores. So you have to go out of the chip. So once you do that, intercommunication between cores, extremely inefficient. extremely inefficient, and you spend a lot of time doing that. So this is what we are. I was saying that block 0 has multiple threads and they have a shared memory. So if you want to communicate within threads of a single block, that is fast. What you can do is this entire shared memory, you can have it in one of the cache, and the threads that are operating in that particular code can just share very fast. But now if you want to share the data between thread of block 0 and thread of block 2, extremely slow. So you have to be architecture aware. That's what they are saying, that whenever you implement something in CUDA or in GPU, you have to be architecture aware. You have to know that what is the size of cache, which threads go to which memory or which core, which threads go to which core, and which threads are sharing data. Right? You have to be very aware about that. So the rest of this involves writing that code, and you can go and look at these examples. We won't be discussing all these examples here. So we'll stop here for GPU. Now it also talks about read before write, hazard, all this. These are all operating system concepts. So we won't really discuss this here. And then thread synchronization is there. It's just a function. Basically you use sync threads. That's a function. When you call this, then all threads stop whatever or finish whatever they're doing, and other threads wait for the other threads to finish. Okay. So this is what we'll talk about with respect to GPU. Now the thing is, there is just one class left. So you tell me what we do, what we discussed in the last class. What interests you? We can do final exam review, although I don't think that's going to be much helpful. Right? But we can do that as well. If you have questions regarding previous materials, you can ask me, or we can discuss some interesting research topics, or we can watch some interesting YouTube videos in the last class. Right? So we'll let you go early today.